Hi everyone. In this video we're going to look at some example questions involving the parallel plates and the electric field between them and how we can do a whole bunch of stuff with them, I guess. Okay, so we'll just jump straight into the questions. Alright, so we've got a voltage of 1000 volts exists between two parallel plates. What is the electric field between the plates if they're separated by 1 centimeter? Okay, so let's draw a picture. Here's our plates. Let's call that positive, that negative. Voltage between them is 1000 and they're separated by 1 centimeter, or in SI units, 0.01 meters. Alright, question is, what is the electric field between them? Well, now we know we have this relationship here. Electric field is equal to the voltage divided by the separation. And so that's 1000 divided by 0.01. You end up with 100,000 volts per meter. If you want to put it into scientific notation, two significant figures, 1.0 times 10 to the 5. There we go. Pretty straightforward. Okay, just applying the equation for the electric field between two plates. All right, so this is 8a. We're going to do multiple parts to this question. All right, so 8b, if an electron of mass 9.1 times 10 to the negative 31 kilograms is placed at the negative plate, what force, and hence acceleration, would it experience as it moves across the gap? Okay, so here's our plates. Yeah, positive, negative, 1000 volts, 0.01 meters, and we're placing an electron at the negative plate here, or just above the negative plate. All right, and what's going to happen is it's going to accelerate across the gap towards the positive plate. Okay, so there's an electric force acting on this electron. So first of all, we've got to figure out what force is that going to be. Now, if we've got the field strength, then the electric force is simply just Q times the electric field. Okay, and from the previous question, we do have the electric field strength. If it will let me go back, there we go. Okay, 100,000 volts per meter. So we know the charge of an electron, that is 1.6 times 10 to the negative 19 coulombs, multiplied by 100,000 for the electric field strength. And we end up getting something on the order of 1.6 times 10 to the negative 14 newtons of force. Cool. All right, so there you go. If you know the field strength and you know the charge that is being placed in the field, you can work out the electric force due to that field. You don't need to use the whole F equals K Q1 Q2 on R squared. This is for the electric force felt between 2 point charges. This is not that kind of scenario. Okay, so we have to use this version of the electric force equation. All right, so we know the force that is acting on the electron. We also have to work out its acceleration. All right, so if you've got a force, how do you work out the acceleration on that object? Think back to Unit 3, Area of Study 3. Think back to Year 11. You've got a force, you want acceleration. What do you use? F equals ma. Okay, Newton's second law. Straightforward as that. Okay, we've got the force that we just worked out. M is the mass of the electron given to us in the question. And so the acceleration is just force divided by the mass. So we've got 1.6 times 10 to the negative 14 divided by 9.1 times 10 to the negative 31. And you end up getting something ridiculous. 1.76 times 10 to the 16. That is a massive acceleration. Okay, due to the fact that the electric force is actually pretty strong, and also the fact that electrons are really, really tiny, its acceleration turns out to be this massive number. Cool. All right. There you go. All right. So if you want a force if you want a force acting on a charge between two parallel plates, you need to know the electric field strength of those plates. Okay. And then you just multiply the charge by the field strength. Okay. So 8c. Hence or otherwise, calculate the speed of the electron as it reaches the positive plate. All right. So think physically about what's going on. The electron is being accelerated towards the positive plate. It's speeding up. Okay. There are two approaches to this kind of question. One is to use the fact that it has constant acceleration. Okay. And things that have constant acceleration, we can use our constant acceleration formulas to work out some details about its motion. In this case, if we use a kinematics approach, well, what do we know? We know its acceleration. It's that massive number, 1.76 times 10 to the 16. We know that it has just been placed there. Okay, so it's starting from rest. So u is equal to 0. We know the distance it has to travel. It's 1 centimeter or 0.01 meters. And we want to know its final speed. So we've got A, U, S, and V. Use the appropriate kinematic equation. V squared equals U squared plus 2AS. Cool. U squared goes away because U is 0. And so V is equal to the square root of 2 times A times S. And if you use the values for A and S that we've got up here, I'm not going to bother writing it down because you can type that in your calculator yourself. You end up getting something like 1.88 times 10 to the power of 7 meters per second. So it is at a speed of just over, what would that be? 5% the speed of light, something like that. Okay, so probably some relativistic effects are going to start taking place here, but we're just ignoring all that for now. Okay, so there you go. That's one approach that we can use because you know the acceleration is constant. You know other things about its motion, how far it's going, what its initial speed was. You want to work out its final speed. That's just a kinematics question. Okay. The other way that we can do it is via an energy approach. Okay. Because this charge is being accelerated in a uniform electric field, work is being done on it by the field. Okay. And we've got some work formulas that we can use. We could use work equals Q times V. We could, if we wanted to, use work equals force times distance, force times the separation, okay, because we know the force, we calculated it before. And then because work is just the change in energy of the object, what's happening here is the work done by the field is going into giving this electron some kinetic energy. So once you work this value out, then you just make that equal to the kinetic energy. You know the mass of the electron. You can then use that to solve for V. Okay. I'm going to use this formula here because we don't have to use any sort of calculated quantities. Okay, voltage has been given to us. The charge has already been given to us. We don't have to use anything calculated like we would if we use the force. Okay, so the work done is simply equal to the kinetic energy gained by this electron. That's equal to Q times V. So Q 1.6 times 10 to the negative 19. V for voltage, so voltage was 1000 volts. And you end up getting 1.6 times 10 to the negative 16 joules. Okay, so that's its final kinetic energy as it accelerates across that gap and reaches the positive plate. Okay, so we know that's kinetic energy. Kinetic energy is equal to half mv squared. We know that it's equal to this number, 1.6 times 10 to the negative 16. And now your job is just to work out V. Okay, so V, what we do is we multiply both sides by 2 to get rid of that fraction. Then divide both sides by m and then square root everything. So it's going to look like square root of 2 times 1.6 times 10 to the negative 16 divided by the mass of the electron, 9.1 times 10 to the negative 31. Okay, just be careful when you're typing this stuff on your calculator. Make sure that you use brackets appropriately so you don't accidentally divide by something wrong. And you end up getting exactly the same thing as the other approach, 1.88 times 10 to the 7 meters per second. Okay, so both approaches work equally well. The problem with using the kinematics approach is you are going to be using a calculated value in the next bit of working out. So we calculated A, that's actually a rounded value. So if you're careful and you keep that value on your calculator somehow, then there's no problem doing it this way. And in fact, that's what I did when I found my final answer here. Okay, I didn't actually use 1.76. I used whatever it gave me on the calculator from the previous question. With the energy approach, it's a little bit cleaner, okay, because you're using values that you haven't calculated, and it's a bit easier to keep things on your calculator when using that approach. But either approach would work equally well, so long as you're careful. Okay, so you really want to start thinking about the energy changes that are happening between these charged plates. Okay, electrons can speed up or slow down. Okay, that's pretty much all that can happen. Okay, they're either going to speed up or slow down. Okay, so next question. We've got two plates separated by a distance of 3 centimeters or 0.03 meters. And the voltage is 13,000 volts. So if that's positive, that's negative, we can say 13,000 volts there. Okay. A 2 millicoulomb charge is held at the surface of the negative plate. So it's being held here, and it's a positive charge. So think about what that charge wants to do. Okay, the electric field is going to tell that charge to go down towards the negative plate. Okay, because positive gets attracted to negative. So if you let that go, it's not going to go anywhere because it's already at the negative plate. It's not going to move. The question says though, with what speed must it be fired towards the positive plate so it just reaches it? Okay, so we have to give this guy some initial speed so that it goes up, okay, and give it enough speed so that it's at the positive plate just as it comes to rest, okay, because what's going to happen is it's going to slow down. This negative plate is going to pull it back towards the negative side. Okay, so it's almost like throwing a ball up into the air. An analogous question with gravity would be, with what speed must you throw a ball up into the air so that it reaches a certain height? That's exactly the same thing here. Okay? And it gives us the mass of this charged object as well. So how do we approach a question like this? Well, I think the easiest way to do it would be in terms of energy. Okay? Most of the questions that you see here are done via an energy approach, especially when we're firing things into these uniform electric fields. So let's just first work out how much work is going to be needed to have, how much work needs to be done for us to move this charge from one plate to the other. Okay, well, we've got an equation to do that for us. Let's just work equals Q times V. All right, and in this case, Q is 2 millicoulombs, so 2 times 10 to the negative 3. And the voltage is 13,000. So the work that needs to be done to move that charge from the negative plate to the positive plate is, what's that going to be? It's going to be 26 joules. Okay, 26 joules of energy required to move that positive charge from the negative plate to the positive plate. Alternatively, another way you can think about it is, it needs to have that much kinetic energy so that when you flick it up towards the positive plate, it will just reach it. Okay, that's how much kinetic energy it needs to have initially to be able to reach that positive plate. Okay? Now, if we know that that's how much kinetic energy it's required to have, from that you can work out how much velocity it needs to have. Okay, because that's just kinetic energy. So we're going to have a half mv squared is equal to 26. And so the velocity required is just us rearranging this. So it's going to be square root of 2 times 26 divided by the mass of this charge, which is 2.3 times 10 to the negative 6 kilograms. And that gives you a value of around 4.8 times 10 to the 3 meters per second. Okay, so it needs that much speed to begin with in order to just make it across to the other side. Okay, so the way we worked it out was we said, okay, how much work is going to be done to move that charge from one side to the other? Okay, we have to provide the work. Okay, the work is being done against the electric field. How much work is that? Well, that's just QV. Okay, anything involving moving charges across parallel plates, you use QV. Okay, and we worked out you need 26 joules of energy to do that. So what you could do is you could provide this charge with this 26 joules of energy in the form of kinetic energy at the start, and that means it's going to have a particular speed. What speed? This speed here. Okay? Cool, moving on. All right, so question 10a. An electron has a charge E, blah, 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 and a mass, blah, blah, blah. These are things we already know. A parallel plate setup is made perpendicular to the ground as shown, with a separation of 20 centimeters. Okay, so here's the ground. You've got one plate here, another plate here, and there's some kind of electric field between them. We don't know yet because we don't know which one's positive and which one's negative. Question is though, if an electron placed between the plates is to be made stationary, okay, it's not moving, which plate should be positively charged? How do you even approach a question like this? What is it even talking about? Okay, well, the hint here is it's talking about this electron being stationary. Okay, now the ground here is significant. That means gravity is playing a role. We need to know which direction down is. Okay, so let's think about the forces that are acting on this electron. Right, so definitely we've got gravity pulling it down this way. Okay, if the electron needs to be stationary, that means there needs to be some kind of other force in the opposite direction to gravity that's going to cancel gravity out, leaving it with zero net force. Okay, so there's got to be a force pulling the electron up this way, and that force is actually going to be the electric force. Okay, now we've got to think, all right, in what possible scenario is this electron going to be forced with the electric force in the upwards direction? Okay, well, you think, are electrons attracted to positive or negative plates? Well, electrons are negative, so negative charges are attracted to positive charges. So what you can say about this then is that this plate here must be the positive plate. It has to be in order to attract the electron upwards. Okay, and it needs to be attracted upwards in order to counteract gravity, which is pulling it downwards. And if the electric field is just right, then the two forces are going to cancel each other out, and you'll end up with no net force, and your electron will be stationary. Okay, so that means the top plate is positive, and the bottom plate is negative for reasons. All right, so that's all that question's asking. 10b. Same setup. We now know that that's positive and that's negative. The question now is, if the electron placed between the plates is to be made stationary, what should be the voltage between the plates? Okay, so our job is to try and work out the voltage here. All right. What do we know about this electron? Well, just like I drew in the previous slide, you've got gravity pointing that way, you've got electric force pointing that way. We know that because this electron is stationary, those forces must be equal to each other in magnitude. So what we can say is Fg equals Fe. All right, what's Fg? What's gravitational force? How do you write that out? Well, if you know the mass of the object, it's just mass times g, which we're assuming here to be 9.8 because we're close to the ground. Electric force. How do we write the electric force, particularly for a charge in between parallel plates? Well, the electric force is simply just charge times electric field. Okay. At this point, we don't really have anything involving voltage, so what do we do here? Well, now you've got to remember the fact that between two parallel plates, the electric field can be written as voltage divided by separation. Okay, so what we can do now I can replace this E here with this expression for electric field. And I get mg equals Q times V over D. Beautiful. Now we've got an expression with voltage in it, which is what we're trying to find. And we know everything else here. We know M, we know G, we know Q, and we know D. So it just becomes a matter of solving for V here. So V ends up being mg D over Q. This expression here might be familiar to you. Try and think about what that might be. mg times a distance. Okay, what if instead of D, I write mgh? Ooh, what's that? That is a value for a particular kind of energy. Okay, so what we've got here is we've got an energy divided by a charge. And if you recall a couple of videos ago, that is the definition of what voltage is. Voltage is energy per unit charge. Okay, don't worry too much about that if this is going over your head. Just worry about the fact that we can derive this equation by making the forces equal to each other, and also using the fact that the electric field between the plates is voltage over D. So now we've got this expression for voltage, put everything in, you get 9.1 times 10 to the negative 31 times 9.8 times 20 centimeters or 0.2 meters over the charge. 1.6 times 10 to the negative 19. You end up getting something ridiculously small, 1.1 times 10 to the negative 11 volts. Okay, and there you go. All right, so go and review that question if that was a little bit convoluted for you. Okay, watch it a couple of times, make sure you understand it. And that's it. That's it for this video. So those are just a few questions that can arise with these parallel plate setups. Mainly they're things like, how much energy is required to move it from one side to the other, or what speed must it have for it to reach the other side, or what speed will it have after accelerating to the other side, things like that. Okay, so these kinds of questions are best done with an energy approach. And so long as you remember the equations for the energy work equals QV, and also the fact that the electric field is equal to V over D, those are really the only things that you need to worry about with these kinds of questions. Okay, so we'll stop there. We've got one more video, which is just a little summary, a little recap of everything. And then after that, we can start looking at some magnetic fields. All right, I'll see you next time.